Our topic 2 is time response. Time response, we call that C of T, through poles and zeros. If we are given the transfer function GS, as in the figure A of example 1 in the previous slide, we solve the time response CT by getting the inverse Laplace transform of the output transform CS. And we know already that CS is equals to RS times GS. So we're going to have this equation. So by partial fraction solution, we need to identify the A and B. So once more, solving by partial fraction equation. From this equation, if we multiply the whole equation by s, then we are going to reduce this equation into this. Okay, into A is equals to s plus 2 over s plus 5. And if we're going to substitute s equal to 0, then we can get A is equal to 2 over 5. Also, if we want to solve for b, we multiply this whole equation by the denominator of b, s plus 5, and this equation will be reduced into this, where b is equals to s plus 2 over s. Substituting s is equals to negative 5, we will get b is equals to 3 over 5. Then we substitute the value of a and b to the equation of CS, then our CS will be this one. Now, take note that this is our output transform equation. Finally, if we get the inverse Laplace of the output transform equation, then we copy the numerical coefficient 2 over 5, and the inverse Laplace of 1 over s is 1. Okay? And for the second term, we copy the 3 over 5, the numerical coefficient, and the inverse Laplace of 1 over s plus 5 will be e raised to negative 5t. And this is now our time response equation. The time response through poles and zeros are illustrated by this diagram. Note that our input pole, the RS, is equals to 1 over s. No? Once more, this is a step function. Okay? So in the S-plane, this input function is located here, no? The input pole at the origin. Okay? And this is in the output transform, we have this, no? For the system 0, meaning the zero of the transfer function is from s plus 2, okay, we locate that into this position, negative 2 position from the origin. Okay, so that's the system 0. And for the system pole, that is the 1 over s plus 5. So in S-plane, it is located negative 5, no, from the origin. Okay, so this is our output transform, and once more, this is our time response, no, output time response. Now take note here that this first term is the forced response, or the input response, while the next term, the second term, is the natural response, or part of the natural response. So time response through poles and zeros, therefore we conclude that a pole of the input function Rs, which is 1 over s, generates the form of the forced response. That is, the pole at the origin generate a step function at the input. A pole of the transfer function 1 over s plus 5 generates the form of the natural response. Okay? So here is the time, the MATLAB script, no, for the transfer function example. And this is the response characteristics. Now, take note, the s plus 2 over s plus 5 is our transfer function. And the graph is given by this, and the pole and zero plot in the S-plane is given by this. The -2 for the 0 and -5 for the pole. Let us have another example. No? So given the system shown, this one, okay, we're going to write the output time response, CT, in general terms, and we're going to specify the forced and natural parts of the solution. Okay? So if we're going to inspect once more that our output transform equation will be is composed of this, no, the forced response and the natural responses. Okay, for this is a third order, no, transfer function. If we're going to take the Laplace transform of this, then we're going to get this equivalent. I want you to notice that whatever is the numeric coefficients in the numerator of the CS, that would be the same, okay? And since if the input is a step function, we're going to have always a 1 for the inverse Laplace here, times 1 lagi ang K1. And on the succeeding terms, we always get the e raised to negative value of the a value, no, of each term. Okay? So this is K2, K3, K4, and the e raised to negative 2t, e raised to negative 4t, e raised to negative 5t. So, by partial fraction, no, we write the breakdown of our equation into this because we have 4 factors. So we separate the factors of the denominator into separate terms and label the numerator of each term accordingly. No, kung may 5 factors yan, edi aabot ka rin ng K5. Kung 6 yan, aabot ka rin ng K6 and so on. And once more, if we want to solve for K1, we simply multiply the whole equation by S to reduce that equation into this. Okay? Notice na nawala na yung S on this side at nawala na rin yung yung K2, K3, K4 terms. And substituting S to be 0, K1 will be 3 over 4. Same solution for K2, multiplying the whole equation by S plus 2 and reducing K2 equation into this, substituting the value at S equals to negative 2. Bakit pa ito yung mga values na sinasubstitute natin? Because we know that is the value of S that will make this denominator 0, as we have defined earlier, that we need a 0 in the denominator if we want to solve for the pole. And we have the same solution for K to 3. Okay? And at S equal to negative 4 to make this 0, then we will get negative 1 over 8. And for K4, we have 2 over 15 for S equals to negative 5. And so, we have this CS. If we put together the value of K that we solved and taking the inverse Laplace transform, then we have this as our time response equation. And once more, if we compare this generated equation from the standard equation, it would be easy for us to identify that 3 over 40 is the forced response, while the other terms are natural response. Note that the natural responses are a function of E. Okay? And for the shortcut method, I think we're going to end. We will continue later. As I was saying in the shortcut method, so without writing each solution for K1, K2, K3, K4, we could simply look directly from this given transfer function, write the equation of the CS. Okay, and from this, by just simply looking at this and by knowing the general format of the time response equation, we could write right away. So how do we do that? So we just we know that we have always 1 as the multiplier for k1, and we always have e raised to 80 for each of these terms. And the exponent here depends on the root from each factor. Okay? So, meaning, uh, say here, no? So, s plus 0. So, it's just like we're having here, uh, let me have this. Okay. So, it's just like writing a e raised to 0 here. Okay, so that is equals to 1. And then for, we have negative 2 here, so we have e raised to negative 2. And then we have 4 here, so we have e raised to negative 4. And then we have 5 here, so we simply write e raised to negative 5. And so on. Kung may dugtong pa tayo dyan, for example, s plus 7, no? So we will write here e raised to negative 70. Okay? And how do we solve for the coefficients k1, k2, k3, k4, and so on? So all we have to do, if we're solving for k1, the denominator of k1 is s. So eliminating s and setting the value of other s equals to 0. So 0 plus 3, that's 3. That's why we have here 3. And then 0 na itong mga ito. So we have 2 times 4 times 5, that will give us 40. And that's it for the value of K1. For the value of K2, the denominator of K2 is the S plus 2. So we eliminate S plus 2 from the denominator and assign negative 2 to the remaining value of S. So negative 2 plus 3, that is 1. So we have 1 here. Okay? And negative 2 here, and then negative 2 here. Negative 2 plus 2 is positive 2, and then negative 2 here plus 5 is 3. So 3 times 2 times 2, that will give us 12 here. So say, solving for K3, no? Our S will be equal to negative 4. So negative 4 plus 3 is negative 1. So we have here 1. So negative 4, and then we have here negative 4 plus 2, it's negative 2. So negative 2 times negative 4 is 8. And then we have here negative 4 plus 5 is 1, so 8 times 1. So that's why we have here 8. Okay? And then lastly for K4, the denominator of K4 is S plus 5. So we eliminate S plus 5 here and set all the other S to negative 5. So negative 5 plus 3 is negative 2. Okay. So we have 2 here. And then mawawala yung negative because of the negative din sa denominator. So negative 5. And then here negative 5 plus 2 is negative 3. And then negative 5 plus 4 is negative 1. So negative times negative is negative. Okay, so we have here 15. Okay, so meaning to say we could write it right away. Okay, our time constant. So let's proceed to the mathematical graph of our example. For our example 2, this is now our MATLAB script. So we could generate the response characteristics and the pole and zero plot. So I want you to take note, no, of the rise time, the settling time. Okay, because these are the characteristics for the first order. Or rather, what we're solving now is the third order, right? Okay, so please note of this response characteristics. And lastly, this is the time response graph of our function, no, this transfer function. No? So notice that this is a step response, okay? And the pole and zero plot. So we have three poles, the -2, the -4, and the -5. And we have 1, 0 at -3. Okay, so I forgot to mention earlier in our example 1, if you may allow me to scroll back. Okay, so we're here again, no, in the time response graph of our example 1. You notice that it's the graph started from 1. No, it's that is the peak value for this example, and it settled at around point 0.4, no? Okay. Note that our input is step response, and want to we expect also a step response at the output of the system. Now, our output is still a step response, but notice that it's inverted. No, it is an inverted step response. Okay, so you might imagine, for example, in a DC circuit. Okay, DC circuit is one example actually of a step response. No output. It's from AC to DC, a step response DC, but not all DC voltages are in positive value, no? It could also a negative value, no? So that's an analogy for a step response that is going down, okay? And going back here once more in our example 2, we also have a step response. And of course, this time, its step is going to a positive step. Okay, so I want you to do the same in your laboratory activity. I want you to solve your poles and zeros of your two circuits, the simple circuit and the complex circuit. And if you will, yeah, and then your graph, no, your time response graph, I want you to observe. I think not all of you have this shape, no. I think some of you has a somewhat oscillating waveform, and we're going to see that on our next topic.